I have a couple quick announcements before we get started today. The first quick announcement is we use this thing in CS109 called high resolution course feedback. Basically goes like this. Have you ever been in class at a mid-quarter evaluation? Yeah. It's too late to change by them, but we're probability people. Maybe we don't need to sample everybody at one point in the quarter. So in CS109, we do the slightly more elegant thing where we're constantly randomly sampling students to get some feedback so we can make the course better. And that means we can adjust immediately. We don't have to wait till like week 6 or week 7 to make changes. So you might get an email that says something like, please submit anonymous feedback for your class. At the end of the course, we see who completed the survey. Of course, we see responses, but we don't see your individual responses not connected to your participation. You guys have said some wonderful things. Thanks for all the positive feedback on how CS109 has gone. There's also 3 things that we want to adjust to give you motivation to actually respond to these because we care about what you say. The first one, can we have more virtual office hours? I brought this up with the TAs, and they're like, yeah. We, in fact, added 4 brand new office hours, and now there's going to be a total of 8 hours that are going to be Zoom only, because there's some people for whom coming to a physical office hour is really difficult. We have so many office hours in CS109. Thank you guys to the TAs. You guys are amazing. Use them. The TAs are there so that you guys can get help if you need it. Some people ask, I wish that the secret code thing was put into the recordings. Aha, I can do that. Every day I can say what is the secret code, and today it is binomial bunny, all one word, all lowercase. Why binomial? Because we have such an exciting celebratory lecture today, and it's kind of about binomial distributions. And then people mentioned that the internet in NVIDIA is not that good. I couldn't just immediately fix that one, but I did start the process of seeing if we can do the deeper fix so that more people can connect to internet at the same time. Thank you guys all for your wonderful feedback. As always, you can follow along from the problem set. There's a place where you can write in your answers to some questions that we'll talk about in today's class, and also you can mark your presence. Okay. Oh, we have such a this is such a celebratory lesson. You guys have worked so hard, and now we can start the process of putting your hard work into nice packages so that you can solve harder and harder problems. You have a couple learning goals for today. When you walk out of today's class, you should be able to recognize a binomial random variable when it shows up in the wild and be able to use it to solve probability problems. And similar for this thing called a Bernoulli random variable. And then finally, we're going to be talking about variance, and you should know how to calculate variance for a random variable. So 3 learning goals. You guys in? Yes. Okay, let's do this. I have a hook for you guys. And the hook is peer grading accurate enough? You know, one of the things that people have thought about for scaling online education is to have peers grade each other. You can imagine it'd be a lot easier for us to grade if we just had you guys grade each other's work. But does that work? And is it accurate enough to be a feasible mechanism for a course? We'll talk about that by the end of today's class, and you'll probably really have to understand variance to be able to understand that discussion. Okay, we're going to get there by the end, but we have to go through a few different steps to get to that point. A little bit of review. In last Friday's class, we introduced this idea of a random variable. And a random variable is the equivalent of a variable but brought to the world of probability. It's a value which is going to take on a number, but it will do so with probability. We don't know exactly what number it's going to take on yet, and so we have to think about the distribution of different values that it can take on. So certainly one of the most important things about a random variable is that relationship between the values it can take on and probability, and we call that the probability mass function. So if we declare something to be a random variable, we'll often use a capital letter to distinguish it from like a non-random variable. So Y, welcome to the world Y, you are a random variable. If that's a random variable, it's not an event. You can't ask what's the probability of Y. You need to ask the probability questions about events. But if you ask any less than, equal to, not equal to question on Y, you will end up with an event. So this is the same as saying the event that Y takes on the value 2. So Y is going to take on value probabilistically. We now have an event, which means we can now ask a probability question. Similarly, Y less than 3, also an event. If you ask the probability of an event, you will get a number between 0 and 1. And that all leads to this interesting, but sometimes confusing at first, conclusion that this is a function. This is a function where you're putting in different values and it's returning you the probability that your random variable takes on that value. And this is the be-all, end-all of random variables. So somebody gives you this thing called the probability mass function, which relates the different values your random variable can take on to its different probabilities. Thank you, person. You've just made our life very simple. Now, any probability question involving this random variable will be straightforward. A little bit of review. Random variables, why are they such a big deal? It just feels like no notation. And the reason they're such a big deal is because it gives other people a mechanism to provide you with this probability mass function. And if somebody gives you a probability mass function, they've done a whole bunch of work for you. Thank you, person who did a lot of work for me. We can now use all that work in our downstream probability tasks. A probability mass function, that relationship between the value a random variable can take on and its probability, can be expressed as an equation. It can be expressed as a graph. It can be expressed as code. There are lots of ways that somebody can communicate this relationship between values a random variable can take on and probabilities. Okay, so random variables, there's a whole bunch of things that we're going to want to know about random variables. Today we're going to cover this spectrum. Every random has a semantic meaning. The most important thing is the probability mass function. And then we already know about this thing called expectation. That's a summary statistic of your random variable, where you boil down all of its interestingness into one number. Hopefully a number that best captures the random variable. Expectation we defined as that is kind of like the weighted average over all the values the random variable can take on. So for every value the random variable can take on, you multiply the value by its probability, and that kind of gives you a weighted center of mass of your random variable. This is a summing loop, as you guys already know. A lot of review. Three things that made expectation so interesting was linearity, expectation of sum is sum of expectations, and this rule of unconscious statistician. We stated these two in a little bit of depth, and we said we're going to hold off on that one till further in the class, which is going to be today. Today we're going to go deeper in unconscious statistician, but not quite yet. It's worth talking about expectation to give you the idea of expectation of a sum. If you have a bunch of data and you want to calculate the expectation of this data, how would you do that? There's no wrong answer to this. Well, there is a right answer to this, but I just mean this as an exploratory question. I haven't told you how to do this already, but you guys want to take a moment and just like get those cobwebs out and get thinking probability. Talk to the person next to you. Think about, how would I calculate expectation if somebody just gave me a data set? What? Well, we have the definition for expectation right there. Wouldn't you oh, how'd you do that? Think about it with the person next to you for just a second, and then we'll talk about it all together. I don't know. How'd you do it? This is just a warm-up. We haven't told you how to do it, but anyone have a guess? I love guessing. I feel like guessing is one way of exploring what you don't know as well. Yes, an idea over here.
Just taking the average.
Yeah, you could just take the average. It turns out that's exactly right. But why? Why is that the right answer?
If you were to calculate like x times p of x for each thing, is like the probability of each thing happening is 1 over the total number of things.
I have a derivation of exactly that idea. So that is right. It turns out you just take the average of all your numbers. That is what the expectation is. That's why some people think about it as the weighted average. And here's why that's a legitimate thing to do. For every probability of x equals x, using the original definition of probability we had, that limit definition of probability, that's about equal to how many times does x take on that particular value divided by how many experiments were there. So if little x is 3 or 10, you're going to say, how many times did 10 show up divided by n? But that 1 over n, it just gets pulled out here. And this sum over x times the count of how many times x shows up, is the same as just saying, let's sum over each of the values and count them once. And so long story short, if you wanted to know expectation from data set, it's just your average of the values. Like you could just sum them all up and divide by n, and that would give you expectation. And this uses a little bit of interesting notation. Certainly, if that didn't just pop out, something worth checking out a little bit more in depth. That does give me a nice way to talk about this expectation of sum is sum of expectations. Like let's say this is x and this is y, and we have a bunch of data on x and y. We could just create a third column, which is the sum of x and y. And it turns out that no matter how x and y is related, the expectation of x, if you calculate that number, take that average, If you take the average of this column, if you add them together, it's the same as taking the average of this last column. And it doesn't matter how x and y are related. No matter what, this law always holds. Linearity of expectation, if you take a random variable and multiply it, you kind of like elongate its probability mass function. If you add 4, you kind of shift its probability mass function. And no matter how you manipulate a random variable, if it's a linear manipulation, expectation still remains easy to calculate. Okay, but is expectation enough? No, expectation is not enough. It's not complete information. Expectation is just taking a whole random variable, bearing it, or summarizing in one number. Like the average of your values is not complete information. It's just the average of your values. The probability mass function, that's your complete information. Okay, that's the end of review. It's been a weekend. I hope you guys are caught up. Questions?
If you know the expectation value of all the moments, does that give us enough information to reconstruct the PMF?
Yeah, so we're going to get into more moments today. Moments is a fancy word for like higher order summary statistics. If you had, there's infinitely large moments, so we can talk about that after class. It's an interesting question. Yes?
When we take the average, do we just assume that everything has the same probability?
Yes, so you're kind of assuming that every single thing was generated. Well, not everything has the same probability, but when you talk about like the probability that x equals like 5, I'm assuming that that's about equal to how many times 5 shows up in the... So count x equals 5 tells me how many times does x actually equal 5 in my data set, divided by the number of things in the data set. That's what I'm assuming.
So would it be correct to say that it's the weighted average and not...
Yeah, expectation. Some people call it the weighted average. Yeah, exactly. It is. That's a very correct thing to do. Okay. Let's jump in. You guys are here. We've made so much progress. We talked about all the counting theory you need. We've talked about the core probability. There's 7 or 8 really, really important ideas that we've talked about. Law of total probability, Bayes' theorem, a lot for you guys to understand. And now we get to relax into the nice, comfortable, happy world of random variables. Welcome to this third section of class. And when we talk about random variables, I'm going to say it's nice and happy because we get to just celebrate what other mathematicians have had and use their great ideas and bring it into our tool sets. And I'm going to bring you through some of the classics. We're going to learn natural phenomena that every person in this world should know about, and these natural phenomena that lead to very, very helpful random variables. Are you guys ready? Whether or not you're ready, we're going to jump in. We're going to start with the most classic random variable, the number one. If I could say everybody in the world should know this random variable, it would be this one. There's lots of stories that involve a very common piece of probability. In fact, we've seen this story before. You have n independent trials of the same experiment. So, and every single trial has equal probability b of being what we call a success. And you want to know what's the probability of exactly k successes. This shows up all the time. We saw it very concretely in the world of flipping a coin. So imagine you're going to flip a coin n times, and you want to know what's the probability of getting k successes. There's very few moments in the world where I actually care about that with coins, but there's so many things in the world that fit this narrative. You have n voters, and they each have a probability p of voting for you, and you want to know what's the probability of getting exactly k votes. And if you can know exactly k votes, you could do k votes, k plus 1 votes, add up those probabilities. So many narratives fit this exact formula. Here's a couple examples. How many heads do you get in n coin flips? It's like n independent trials, and you want to know how many successes you get in those. If you randomly generate a bit string of length n, and you want to know how many ones are generated. If you have 1,000 computer cluster, and you know that the computers crash independently with some probability, and you want to know what's the probability of different numbers of computers crashing, you can calculate that. And in fact, when computer scientists first made Google, and they started to first make large social networks, they would have their servers hosted on thousands of computers. And it was the people who really understood this natural phenomena who were able to predict, okay, when are our servers going to be crashing? And they were able to identify how much extra load that they would need to know. Voting for a candidate, we mentioned quickly. And we'll talk about this later, but if you want to make sure that a jury is not unfairly selected. You could use this theory to figure out if things are probabilistically out of distribution. All these stories really involve the same key metaphor. This metaphor of I have a coin, and I'm flipping it n times. It's got a p probability of being heads. I want to know what's the probability of getting exactly k heads. And we've seen that before in class. And in fact, it's so important. I spent a lot of time trying to make a really cute thing in the course reader so you can go through it one by one. And you can see exactly why, if you have 10 heads, n equals 10 heads, and has a probability of 0.7, that the probability of getting exactly 6 heads is going to be this beautiful, beautiful equation down here. The probability exactly k heads in n coin flips is going to be n choose k, p to the power of k times 1 minus p to the power of n minus k. And you don't have to have memorized the derivation. That's kind of the point here. But if you're curious about the derivation, you should know all these steps because it's a beautiful combination of all the core probability we've learned so far. We talked about this earlier in class. The important takeaway today, though, is what if you didn't want to rederive this every single time you saw that metaphor? What if you just wanted to package all of that work we did when we did the n coin flips into a beautiful equation that you could use in all other different contexts? Somebody beat you to it. And in fact, back in the day, somebody was like, this story of n coin flips with a probability p of coming up heads shows up so much in different probabilistic real-world examples, I want to make a random variable around it, and I'm going to call it the binomial random variable. Huzzah! Okay, anyways, a long story short, this person who invented this binomial random variable that we're going to learn about today is called Jacob Bernoulli, also known as James, a Swiss mathematician. He's one of the many mathematicians in the Bernoulli family. The Bernoulli random variable is named after him, even though he is most famous for identifying the binomial random variable. This is kind of cute. When I was in PhD, I had an advisor. That's like my advisor. And then the advisor of that advisor, Daphne Culler, is like my great-grandmother, or my grandmother. And then if you keep going, there's like more and more advisors that are in my heritage. And he's my academic great to the 12th grandfather, which is kind of cute. Not that important. And I think I went with celebrity look-alike Ice Cube, but I don't know. Okay. The great thing here is, if you can recognize anything that fits this story, n coin flips probability p of success, we care about how many successes you get to just write this line in your problem set, and you inherit all the mathematics related to this story. You can say, I have a random variable, I'm calling it x. It is distributed as a binomial. We write bin for binomial. We don't have time to write the whole binomial. No one's got time for that. Bin is enough. And this binomial always takes in 2 parameters. Your story is allowed to have 2 pieces that you can define. How many coin flips are there, n? And what was the probability of a success on any trial, p? Anytime you recognize a story, you write that line, and you inherit all the mathematics because everyone knows the mathematics around x. And if they don't know it, they should learn it because it's such a beautiful natural phenomenon. Most importantly, if you declare x to be a binomial, you automatically inherit this beautiful equation. And this beautiful equation says, you've told me x is a binomial. I will tell you the probability that x takes on the value k. You don't have to rederive it. This probability mass function for a binomial is already known. The derivation's in that multiple coin flips question. It has some terms. This is called the binomial term because it's the multiple coefficient. And it's just going to be this binomial term, p to the power of k, 1 minus p to the power of n minus k. You've already told us what p is. You've already told us what n is. And when you put in k, you've got all those 3 values, and it can give you the probability that x equals any value. Now, if you go to our course reader, under random variables, you'll find the binomial distribution. Huzzah! And here it is. And you can try different values of n and different values of p. And as you try different values of n and different values of p, it will change the probability mass function that's given for you. Each of these columns can be calculated using the PMF equation. But they each have their own value. This is saying if n is 23 and p is 15, the probability of getting exactly 5 successes is 0.137. You can use this tool, go for it, have a good time, get some intuition. Okay, probability mass function as a graph. I'm going to show you a couple. This is when n is 20 experiments, probability of 0.6 of getting heads, and this is the chance of getting 7 heads, and 8 heads, and 9 heads. Isn't that just a beautiful little curve? Like, let's just take a moment and appreciate the aesthetics. Ah, good looking curve. Okay, now it's not always the same. You know, if you took exactly that same n but changed p to 0.1, then we get a new curve. We get, here's the probability of getting 0 successes. That's much more likely now that the probability of success is 0.1. And people can give you stories with different n's and different p's, and you will automatically have access to this graph. Okay, I got a little extreme there. Let's calm down. Okay, now I want to revisit this question we talked about before. We said, let's say you flip 3 coins. Every coin comes up heads with probability p. X is the number of heads. Now I'm going to define x to be a binomial. And as soon as I define x to be a binomial, I know these things automatically. I know that the probability of x equals 0 is just plugging into that equation. You know, n was 3, here k is 1, and p is equal to 0.5. And if you just put those 3 numbers together, you get answers for all these. We've derived these before, but you could have solved this problem without deriving it. If you had just recognized the coin flips as a binomial expression, you're done. You don't have to derive anything. You just have all your answers. Okay, let's try another example. Here's what a binomial question could look like in the wild. It's hiding, it's lurking, it's not telling you it's a binomial distribution, but if you can recognize the binomial distribution in the world, then you can solve these problems really easily. In fact, the solution just becomes 4 quick lines. A real world problem. 1,000 ads are served. Every ad is clicked with a probability of 0.01. Otherwise, with a probability of 0.99, people are ignoring the ads. Most of us ignore the ads. Come on, let's be real. And then you can ask the question, what's the probability of exactly 10 clicks? And if you wanted to answer this question before you knew about binomial random variables, you'd really have to go back to doing all of this work. You would have an answer that would be this long, and you go through all these steps. But now you know about a binomial random variable, you can answer it in 4 lines. You say, I know h. It's going to be the number of clips. It's a random variable. And it's not just any random variable. Because of the story, this is the same as 1,000 coin flips, each with a 0.01 probability of being heads. And the question is just asking what's the chance of 10 heads. And because of that, I can declare h to be a binomial. This is a powerful line. I'm saying I've seen the binomial metaphor in this story. And once you've written this line, you get this equation for free. You know, the probability that h takes on the value k, and you get that it's going to be 1,000 choose k, 0.01 to the power of k, and 0.99 to the power of 1,000 minus k. Then if you plug 10 in for k, what's the chance of getting exactly 10 coin flips? You know exactly what that is. Amazing! You guys don't have to derive things, but now you have a new challenge. You have to recognize this natural pattern in the wild. Yeah, questions?
If you have 10 probability that there were exactly 0 clicks or 10 clicks, would it just be the probability of 0 clicks plus the probability of 10 clicks?
Oh, that's a deep question. Okay, so far with binomials, we can just say what's the probability of exactly 10. But let's expand our abilities. What if you wanted to know the probability of exactly 0? So the probability that h equals 0 or h equals 10. Aha, a challenge. And an important challenge that you can solve with what you've got so far. And in fact, so important that I'm just going to give you guys a second to think about it. Talk about with the person next to you. Either solve this or come up with a question regarding what we've talked about so far that you'd like to see clarified. Anything confusing? Talk about with the person next to you or try and solve this one because it'd be nice to be able to do more than just exactly 10 clicks, hey? Okay, go for it. Okay. Before we go into answers, anyone come up with a clarifying question that they think is relevant? You're like, why? Here's a good question. Why did no one tell me about the binomial before? It's so present in so many natural phenomena. Maybe you've heard about it before. But if you hadn't, what a beautiful day in our lives. Okay, how are we going to solve this problem? H equals 0 or H equals 10. You can solve it with the tools I've given you. What's the idea here? What makes probability of OR easy?
We can just split them up into the probability of getting a 0 plus probability of getting.
But why can you do that? You can't always just take an OR and turn it into plus. Something has to be true.
They're mutually exclusive.
But are they? I challenge you on that. No, sorry, that was too much. They are, you're absolutely right. They are mutually exclusive. Because it's not possible for H to both be 0 and 10. Those are different numbers. H is either 0 or 10. The outcome spaces are mutually exclusive. You can't have both things happen at the same time. And because of that, the probability of OR becomes easy. It becomes the probability of this times the probability of H equals 10. I was going to save this till later, but I'm so excited now. I'm going to tell you, we can answer other questions. What if you care about the probability of less than 10 clicks? You think this is like a failed campaign. We haven't talked about less than 10. Well, how are you going to do that? No, think about it. No, don't talk to your partner. Just think, how would you do that? Less than 10. Be inspired. Feel the inspiration. Okay, hopefully you're inspired to come up with this. Right, you've got probability that H equals 0, or H equals 1, or H equals 2, or H equals 9. What about 10? Not less than 10. Man, those off by ones are killer. And you're like, each of these are mutually exclusive. You can't be 0 and 1. You can't be 0 and 2. You've got to be only one of those numbers. And so this is going to be equal to the sum looping from x equals 0 up to and including 9, the probability that H equals x. Wild. Okay, anyways, we've gotten ahead of ourselves, but I'll just leave that up there. This was the probability that H is less than 10. Which you might care about too. Oh my gosh, there's so much we can do once you know it's a binomial random variable. Yeah, question?
Is there a closed form for b of h less than 10?
No, this is it. Oh, and what would you do for h equals x? I'm like, why can't you just stop there, Chris? We already have the equation for that. Because we declare it as a binomial, you automatically inherit this beautiful probability mass function, which is the probability that h takes on a particular value. And you would just plug that in 9 times. Question is there a shorter way of doing it? No. You must do it 9 times. Hopefully you have a computer. If you have a computer, 9 times, not a problem. In fact, speaking about having a computer, I love that you guys are computer scientists. It makes teaching this so much more reasonable. Because I can tell you, haha, stats just gives you a way to do this. Stats is a Python library. You can say from SciPy import stats. This is a lot to write, but you'll be very happy because after you write stats.binomial.pmf, it gives you this equation in Python. You have to say what is n, and you have to say what is p. Those are the 2 parameters of your binomial. And then you have to also say what is k. So if you have 1,000 ads with a 0.01 probability of anyone clicking, the probability that exactly 10 ads are clicked on are ta-da! It's a global thing. We're not the only ones who know about this. Somebody told Python. And you could ask any question you care about, any value of n, p, and k, and you can get an answer. So certainly if I wanted to calculate this, I would write a simple for loop, run it 10 times, and I would do stats.binomial.pmf, I, comma, 1,000, comma, 0.01, and I get the probability that it's less than 10. Whoa, amazing. So I meant to just give you guys a chance. This is super important that you can do this. Now it's your turn to do it. I've done this a lot, but this is like the 10 out of 10. You must be able to do this walking out today's class. 1,000 ads serve. Probably 0.01 of getting somebody to click on one. What is the probability of exactly 5 clicks? You have to be able to solve this. You have to be able to answer a question like this as of now. And so if you don't, good time for a question. Okay. What do you have to do? 4 steps. Declare a random variable. I could call it h for the number of people who click on an ad. Declare h to be a binomial. I would say it has n 1,000 and p 0.01. And then I want to know what's the probability that h equals 5. And you could just go into, let's say, your favorite pset app. Now we find out if my Wi-Fi is working. Okay, nice ad, Chris. And you can do n equals 1,000, p equals 0.01. Whoa, 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 no one can see that. Can you guys see that now? I could say the probability of 5 equals stats.binom.pmf for probability mass function, and 5 comma n comma p. And then in theory, if I print this, we'll find out if I remembered all of those commands off the top of my head. Oh, buggers, it's not loading SciPy. Okay, Do you know Python's also on your computers? Python, let's run all of you guys. Stats is not defined. I don't know why I didn't copy the top line. Oh, has no module called Python, okay. Python 3.9. I recently got Python 10, and my Python 10 doesn't have stats. That's not important right now. What is important is now I've run this on my computer, and it told me that 0.37 is the probability that my random variable equals 5. So this is what you should feel comfortable doing. Beauty of recognizing the binomial random variable. You see a question like this, and you don't have to rederive everything. You inherit the probability mass function. It's even in SciPy. Okay. Do you guys feel like you guys could do that in the wild on your own? I see a bunch of nodding heads. That makes me very happy. Okay. Okay. You know, you could put this into the problem set app to see this graph and just look it up on the graph. That's one way to do it. But obviously, I'll use SciPy. Let's try this again. You guys kind of know where I'm going, but I just want to give you this idea that it shows up in lots of places. 7 runs of a program. Each run crashes with probability of 0.3. What's the chance of exactly 3 crashes out of your 7? So maybe you have that program that has some intermittent bug, and you're trying to figure out, will it pass the auto graders when I submit it to CS111? 7 runs of program. Each are independent. Each crash independently with probability of 0.3. What's the chance of exactly 3 crashes? How would you solve this? Talk about it with the person next to you while I get the board ready. Okay. Who here, there's like a bunch of random variables. There's a binomial, there's a Poisson. Sometimes something's not a classic random variable. You just have to derive it from the beginning. Who here thinks this is a Poisson? You're like, Chris, you haven't taught us that. Not me. Who here thinks that it's like no classic random variable? We have to derive everything from first principle. I love it. Who here thinks this is a binomial? Yeah, rockin'. Okay, so if you want to solve this problem, you just say x is defined as the number of crashes, and the next line in your solution is x is distributed as a binomial. So this is you declaring it's a binomial, and you have to give me 2 parameters, n and p. Can you guys just shout out what's n? Aha. Wait, how come it's not 3? You're like, because that's not what it is. N is how many experiments there are, not how many successes you're looking for. What's the probability of success in every experiment? Now this is kind of interesting. We've defined success as a crash. And in what way is crashing a program a success? Yeah.
The event of a crash happening.
Yeah. It's the event of a crash happening is what is the thing we're trying to count. But anyways, it's like the heads equivalent. We're thinking of crash as being like the equivalent of getting a heads on our coin flip. And then you define what's the question asking. The question's asking what's the probability that x equals 3. And at this point, you could just plug in the binomial distribution. You know, it's 7 choose 3, p, which is 0.3 to the power of 3, and 0.7 to the power of 7 minus 3, which is 4. And I know people over there might have lost this, but it's exactly what you expect it would be. Cool, and you're done. You could put this into a calculator. You could use the SciPy function we just showed you, which does all of this in one go. You now have the ability to calculate binomials. You don't have to, like, if you had to derive the binomial when you saw a question like this, your midterm would be brutal. Okay. Oh, here's a fun one. Binomials, they're everywhere. So here's a Galton board. If you guys haven't seen a Galton board, I actually have one over here. Look really closely. No, you can't see that. We're going to use the dot cam in just a second. People who do the dot cam, can you help me get set up? But just in a second, don't switch over yet, but just know it's coming. A Galton board looks like this. There's all these pins, and we drop these balls on the pins. You're like, what does this have to do with probability? Wait for me, wait for me. When the balls hit the pins, they either go left or right. And every single time they hit a pin, we think they have an equal probability of going left and right. Oh, marbles, whatever. Every single pin is independent, so what happens on this pin doesn't change what happens on the next pin, and eventually your ball ends up in a bucket at the bottom. And we're not going to just drop one marble, we're going to drop a whole bunch of marbles. In fact, we're going to be dropping millions of these ones. Wait, they never fall out. If they go all the way to the right, they end up in this bucket. So I'm going to define R to be how many I'm going to define B to be how many times did you go right? And how many times can you go right? There's 1, 2, 3, 4, 5 chances where you could go right or left. And so I'm going to say B is going to be the number of times when I chose to go right. If I choose to go right 0 times, I'll go left, 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 I'll end up here. If I chose to go right 5 times, so in the first level I go right, in the second level I go right, in the third level I go right, fourth level right, I go fifth level I go right, I'll end up here. If the number of times I choose to go right is 2, no matter where I choose to go right twice, I'll end up here. So if I go left, left, right, left, 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 right, right, I'll end up here. The number of times you choose to go right determines which bucket you end up in. And the beautiful thing is, the number of times that you choose to go right is going to be binomial. There's 5 experiments, and each experiment has a 0.5 chance of giving you a right. And you can figure out the probability of a marble landing in each of these buckets using the binomial probability mass function. The probability that a marble goes into this bucket is the same as a binomial with n5 p equals 0.5 being 0. And you can calculate what that is 0.03. You can calculate what's the probability of it going into the 1 bucket. That's going to be 0.16. So you can do the same thing for all the different buckets. And you know exactly what this probability mass function is. Can I go to the dot cam? Is that a reasonable thing to do right now? Oh, yeah. OK. Let's see if we can figure this out, though. There's this thing called a dot cam. Wow, what a time. Wait, I need this to be balanced, though. Oh no, did I press the off button? I just got it where I wanted it. Oh man, dot cam, did I break you? No, you're back! You're alive. You are alive. Amazing. Oh, it's upside down. That's hilarious. Imagine if you flip this upside down. So this is just kind of like the binomial distribution's prediction of how many marbles or the probability of a marble ending up in each bucket. And look how good a prediction is. Oh, how beautiful. OK, let's do it one more time. Wow, that's it upside down going into. I can't flip it upside down, can I? No. OK, you guys just have to get used to looking at the world upside down. Wow, amazing. The probability predicts it so well. Yes, thank you, technicians. We really appreciate it. OK, back to the slides. OK. Here is a real one, not a small one, but a really big one. And they built this somewhere, and they made this huge construction. And there's this music playing. It goes, do, 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 yeah, 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 yeah. All your marbles are going up to the top of your Galton board. All of them are going, where are they going to land? Which bucket? Oh my gosh, they're hitting pins. And the number of rights they take, binomial distribution. All of them going, go, go, go. And through all of this chaos, such predictable order. It comes, is it going to follow the distribution that the binomial predicts? Yes! Again? Is it going to do it this time? I don't know. Does probability lie? Sometimes people lie with probability, but this time the probability is right. It goes, it goes, it goes. You get the binomial distribution. Oh my gosh, from chaos you get such order. Wait, that's actually the next example. It is such a beautiful thing in this world that from all of this uncertainty that you get such incredible order. And it's a natural phenomena. You now know what to call it. It's the binomial distribution. And it shows up in lots of other places. For example, what's binomial distribution doing in my basketball game? Let me tell you. If you don't know this, when people get to the playoffs in basketball, they play 7-game series. And in those 7-game series, if you win 4 of those games, you have just won the series. And so often people care not about the probability of just winning 1 game, but what's the probability of winning a 7-game series. So out of those 7 games you play, what's the probability of winning 4 or more? My claim for you is that if you wanted to derive this from first principle, it would be very, very hard. You would have to kind of go back to the whole coin flipping derivation. But if you can see the binomial here, your life is a lot easier. So take a moment, look at this question. Can you see the binomial? So the Warriors are playing the Bucks in a best-of-7 series. Sorry, this was before I knew who they actually played. They won. How crazy is that? Wow, it's our local basketball team. Yay. Okay, what's the probability of winning at least 4 games? And see the binomial. It's 7 coin flips. And a head is a win. So x, my random variable, I'm going to be finding to be the number of wins in my 7 coin flips. And as soon as I do that, my next step is to let the whole world that x is binomial. The number of coin flips is 7. The probability of a heads on each coin flip is a 0.55. But that just tells me the whole distribution for what's the chance that they win 0 of those games? What's the chance that they win 1 of those games? What's the chance that they win 2 or 3? 4 games means that they win the series. 5 games also means they win the series. 6 games win the series. And 7 games also means that they win the series. Somebody's like, wait, don't they stop playing if they win 4? Like they don't bother with the next 3? Like if they win, no one plays those other 3. In my world, they do play those other 3. And it doesn't change the outcome of this probability experiment. That'd be kind of fun, but tiring for the players, and maybe they get injured, and then we'd be sad. Okay, I'm glad that they do it the way they do it. And this will allow us to solve the problem of the probability that they win at least 4. The question is asking, what's the probability x greater than or equal to 4? And we don't have an equation for that. We only have the probability that x is equal to 4. But for those of you guys who've been paying attention to mutual exclusivity, you know that this is the same as saying what's the probability that x equals 4 plus the probability that x equals 5 plus the probability that x equals 6 plus the probability that x equals 7. Every single one of these equations is given to you by the probability mass function. You can ask, what's the probability that binomial with n7 p 0.55 equals 4? And you can ask it for 5 and 6 and 7. Since they're mutually exclusive, we can add them up, and this would be the probability that they win the series. So just to put that into the slides, what I'm saying is define a binomial with 7 games and 0.55. And the probability mass function will tell you what's the probability of 0 wins out of 7. Not very likely. They're quite good. 1, 2, and 3. And what I'm saying is we're going to add the probability mass of 4 with the probability mass of 5 with the probability mass of 6 and the probability mass of 7. That's what adding up each of these things is doing. It's looking up each of the columns and adding them together. If you did that, you could write it as a for loop. And a for loop in math looks just like this. And everything in the for loop, we're plugging in the binomial distribution probability mass function. I is the index of my for loop, and it shows up in this probability mass function where k would normally show up in the PMF. And if you put this into something like SciPy, and since what we could do is we could say for I in range 4 to 7, or 4 to 8. I think if you do this, you get 4, 5, 6, 7, yeah. For I in range 4 to 8, we're going to, I need to get a sum. For I in range 0 to 8, sum probability plus equals stats.binomial.probability mass function. I, because that's the number of wins we're looking for. there are 7 games, and each one has a 0.55 probability. So this is going to loop 4 times, and I will take on the value 4, 5, 6, 7. And each time we'll say, what's the probability exactly I wins? Add those all together, and we have some probability, and the chance of them winning at least 4 games is 61. So even though it's pretty even chance for any one game, the chance that they win the whole series is pretty large. I'll just make that quite big, because going from math understanding to code understanding, I think is something that you probably wouldn't have seen in other classes, and I think it's very important if you want to start making tools around this cool theory that we're learning. This is like theory to practice in one screen. Question? Yeah. Yes.
Is it possible for a random variable to take on multiple different values and not be mutually exclusive?
No, it's always mutually exclusive, because we think of it, if it takes on one value, it just can't be another one. If they won 4 games, they can't have won 6 games, because we think equals to as being just that value. Such a good question. So always mutually exclusive, can always use the sum trick. Yes?
How would this differ if they had to stop playing after?
Well, they do. And this is still the right answer, even though they stop. I'm so glad you asked that, because it's such a common problem when people do probability to get tripped up by the fact that they stop at 4 games in the real world, that I wanted to take a moment and talk about this. I've seen so many students make this bug. Can we just talk about it together? Here's how people make this bug. You want to know what's the probability of at least k successes in n independent trials. X is going to be the number of successes in n trials with probability of k. So x is our binomial random variable. Some people say, what's the probability that x is greater than or equal to k? They don't use the fact that it's a binomial random variable, or they just think of it like this. I want to choose k slots for my successes. And then I'm going to say, in those k successes, each one has a probability p of being a success, right? And there's k of my successes. So you choose your k successes, you choose where they go, and for the other ones, they could be successes or not successes. If they're not successes in the other slots, then you still have exactly at least k successes, because we've chosen k of them to be successes. If they end up being successes, great. We had more than k successes. That also fits this definition. Does this seem like a pretty reasonable thing to do? K successes each have probability p. You can choose where they go. Turns out this is not the way to solve this. You still need to use this sum from I equals k to n and the binomial probability of your random variable equaling exactly I. And a good way to show that this is a bug is to first think about what happens if the probability is 1. So if your probability is 1, let's go back to this equation. You have 1 times itself k times. That's going to be 1, right? But n choose k is going to be something greater than 1. And this is going to say that the probability that x is greater than k is going to be a number greater than 1. And it turns out that doesn't work. You can't have a probability that's greater than 1. So if this case fails, then there must be something wrong with this outcome. The reason we have this n choose k in this binomial distribution probability mass function is because each of those outcomes of heads and tails were mutually exclusive. If you had tails, heads, heads, tails, let's say there's 4 trials and you're looking for 2 heads, heads, tails, heads, tails. Each of these outcomes were mutually exclusive. There is n choose k of them, but because they're mutually exclusive, we could add the probability of this row with the probability of this row, and every single row ended up having p to the k times 1 minus p to the n minus k. So that's why we could, if you added up p to the k times p to the 1 minus k, n choose k times the same as multiplying n choose k by the probability of any one row. So it relied on the fact that these rows were mutually exclusive. In this derivation, you have rows where you have the heads are defined, and you have blanks where there's no heads. And you're saying, I'm going to add up all the rows. The probability of every row is just the probability of the heads, and I'm going to not care about what shows up in these other slots. But it turns out you could end up with let's say we put a head here and a tail here. With some choices for these other slots, you end up with non-mutually exclusive rows, which means you can't use this n choose k multiplier that we used in our binomial distribution. Okay, I think that answers one bug, but I believe your question was slightly different. Your question was, what happens if they stop after 4 games? So let's think about the case where the Warriors have won 4 games, the first 4 games. You have heads, 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 heads. And what I've done is there's 3 more games, and I've got every combination of like heads, tails, heads here. You'll see heads, 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 tails, 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 heads, heads, heads. Every 2 to the 3 ways shows up here. My claim for you is that if you added up all of these probabilities, that is the same as the probability of just heads, heads, heads on its own. And there's a bit of a law of total probability thing going on here. You know, like these background contexts don't matter, and I'm looping over every single possibility and adding them together. And so by a law of probability argument, these things end up being equivalent to the probability of heads, 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 not worrying about the other 4. That is a very complicated argument. But if we thought about this not mathematically but intuitively, I'm saying, all these cases are going to exist, but when these ones exist, what you'll experience in the real world is just they stop playing. And even though I've thought about the futures of them, what would happen if they did play, in the real world, you observe them stop playing, but it doesn't change the fact that this derivation that I have over here is the correct one. So thinking about 7 trials and the probability of getting I successes out of those 7 trials. Yeah?
So that in that case, it means our n is going to be 4, not 7, right?
Yeah, but in my thing, I treat it as 7, and it just made this case happily work out. If you wanted to just think about this case on its own, I guess you could say, okay, if you wanted to derive this with n of 4, you would say in 4 experiments, what's the probability of getting exactly 4 successes? And then in 5 experiments, what's the probability of getting exactly 4 successes? No, that's problematic because they're not mutually exclusive. But so my derivation, I always play out all 7 games. I always set n equals 7 and p equals 0.055, which means I'm always making the Warriors play even though these are ghost games. And in reality, they wouldn't play them. And the reason that this doesn't affect it, like the fact that they're ghost games versus not ghost games, doesn't affect the probability that this will give you the chance that they win. Okay, good questions. Okay, big picture now. If you can recognize a binomial distribution in the real world, you get so much for free. You get all of these things that you get in the course reader for free. You get the PMS equation. You get that the expectation is just equal to n times p. And you get a little bit more. We're going to talk about that little bit more after our pedagogical pause. So I'll give people 2 minutes to just take a break, solidify and crystallize what we've learned so far before we walk into our next piece of today's class. Okay. Fantastic. That was such a good question about hey, they don't actually play 7 games. They sometimes stop after 4. Why does that not matter? And I feel like that's best explained by just kind of enumerating over a whole bunch of possibilities. So we're going to write that up for people curious about that detail. And we'll make an ed post for you guys. Okay. As we last left off, we learned about the binomial distribution, one of the most beautiful natural distributions in the world. You can use it anytime you recognize it. You'll start recognizing a lot in the world. But let's go back to Jacob Bernoulli. He's like, I invented one of the most useful random variables in the world, and they didn't call it the Bernoulli random variable. He's like, sad face Bernoulli. And he's like, can I have a variable named after myself? And people, in fact, were like, OK, you can have one. And they kind of gave him the most boring random variable, to be honest. He gave him the special case of the binomial where n is equal to 1. If n is equal to 1, what are the different values that your random variable could take on. If x is the number of successes in one coin flip, it can be a 0 or a 1, which is kind of cool. He kind of gets the probabilistic equivalent of a bit. But anyways, yeah, he gets the Bernoulli random variable is named after him. Special case of the binomial. If you declare x to be a Bernoulli random variable, it will take on the value 1 with probability p. You have to say what's the probability of heads. And it's going to be a 0 with probability of 1 minus p. If you find something that is basically a single coin flip and you're measuring number of heads on a single coin flip, which doesn't happen all that often, but it's very important to give you this terminology because it does show up again in machine learning literature a lot. You define x to be a Bernoulli random variable, and you say x is a Bernoulli with probability p, probability of success. The expectation of this random variable, it turns out, is equal to exactly p. And here's a couple examples. You flip a single coin, and you want to know number of heads. You get a random binary digit, and you want to know whether or not it's a 1, and you want to know the outcome of it. Whether a single disk drive crashes, and whether somebody likes a single Netflix movie. It's a special case of Bernoulli random variable. I'm not going to go too much into it because I think a lot of this is pretty self-evident. You can just define, if something says like, I serve a single ad, and people click with a probability p, and they ignore it with probably 1 minus p, c is going to be a 1 if the ad is clicked. You can declare c to be a Bernoulli. And it doesn't buy you that much. The binomial buys you so much, and the Bernoulli really just doesn't buy you that much. And you can think of though as if a Bernoulli is a 0 or a 1, you can think about the binomial as being a sum of Bernoullis, and that's actually quite helpful. So you can imagine if this Bernoulli is going to be like, there's 4 coin flips, and this Bernoulli represents whether the first coin flip was a head. It'll be a 0, 1. This Bernoulli represents whether the second coin flip's a heads. It'll be a 0, 1. This third Bernoulli represents how many coin flips are heads in that third coin flip. It will be a 0, 1. This is how many coins are heads in the fourth coin flip. It will be 0, 1. You can think of the binomial of 4 coin flips as the sum of each of those Bernoullis. It's going to be the sum of those 0s or 1s. 0 if it's tails, 1 if it's heads. You add all those up, and you get your number of successes. OK. And I'm going to give you a reason to have learned the Bernoulli. We're going to use the fact that we now have a Bernoulli to come up with a simple derivation for the expectation of binomial. I told you the expectation of binomial random variable is just n times p. Now I'm going to derive it for you. So x is going to be our binomial. But we know that x is just going to be the sum of a bunch of underlying Bernoullis. So xi is going to be a 1 if the ith coin flip is a heads, and it'll be a 0 if the ith coin flip is a tails. And if you sum up all those 0s and 1s, and there's n of them, you'll get the number of coin flips. This is the very first time we've really seen a random variable defined as being the sum of other random variables. You add up all these 0s and 1s, and you get x, which is the number of successes. And that's quite interesting, because if you want to do expectation of x, you can now replace x with that sum. You can say, this is really the expectation of the sum. One of the properties that I reminded you guys of at the beginning of this class is the expectation of the sum is the sum of expectations. Another way of thinking about that is expectation always has the keys to the house. Like, look at this beautiful house. Expectation is like, hey, house, I just want to get in there. And like, as soon as expectation is on the outside of the house, it's like, hi, guys, I'm inside. Because the expectation of the sum is the sum of expectations. What's the expectation of a single coin flip? A single coin flip, which has a probability p of being heads. Well, let's think about it. Let's say the expectation of yi. Yi can take on 2 values. We're going to take each of those values and multiply them by their probabilities. One value that yi can take on is 0. You can get 0 coin flips in your ith coin flip, 0 heads in your ith coin flip. What's the probability of getting 0 coin flips? Doesn't matter. It's multiplied by 0. What's the other outcome of the ith coin flip? Yeah, 1. These Bernoullis, separate from binomials, special case, they can only take on values 0 and 1. And what's the probability of getting 1 heads in a single coin flip? P! Yeah, P is the probability of getting a heads. So this whole expectation of yi is just equal to P. This 0 times whatever, 1 minus P, goes away. Because expectation of yi is equal to P, we can just substitute it in there. And this is going to say the sum from 1 to n of P is going to be the expectation of your binomial. So the expectation of binomial is n times p. Very hard to derive if you didn't use the fact that the binomial is actually the sum of these Bernoullis. So even though the Bernoulli is just really not that interesting of a random variable, sometimes it shows up in proofs like this. And also, you just kind of need to know it if you want to be like a conversational probabilist in the world. So anyways, you have this binomial. What a beautiful curve. And then you have the Bernoulli. It's like, I'm 0 or 1. And I'm 1 with p, and I'm 0 with 1 minus p. Deal with it. But anyways, it's a random variable too. And it's a class of random variables. You can declare things to be Bernoullis. OK. So here we are. We will continue to grow our understanding of natural phenomena and classical ideas of random variables. But before we go any further, we need to talk about other things you can do with random variables. One thing we know you can do with random variables, you could summarize it into a single number, expectation. But expectation is a very lacking number. What if we wanted to add a second number so we could summarize the random variable a little bit more holistically? Expectation leaves so much to be desired. In fact, a lot of people who lie with statistics are lying with expectations. And my question for you is, I want you guys to invent another summary statistic to go beyond expectation. And we're going to start with a story of peer grading. So we're going to think about somebody who is being peer graded by other people and they want to get the grade that they deserve. Imagine 3 different graders. You have grader A. If this is the true grade that somebody deserves, this is the distribution of grades that grader A gives. Sometimes they give the grade that is deserved, but sometimes they give a grade that's way lower and sometimes give the grade that's way higher. Here's grader B, and here's grader C. I want to find out if we can tell a story of who we want to be grading us and figure out what we would like to measure in order to talk about grader accuracy. Now think about this for a second. Do you want grader A, B, or C grading you? The red line's the grade you deserve, and this distribution is the grade that they're giving you. So C is kind of a jerk. You're like, I deserved a 70, and it's like 50. I'm like, but I deserved a 70. So I think a lot of us would be like, OK, C, if it was the other way around, they were giving us grades higher than we deserved, we'd take them. But because they're giving us lower grades, we don't want it. A and B have exactly the same expectation. In expectation, they give you the exact same grade. But who wants to be graded by person A? And who wants to be graded by person B? There's not a wrong answer here. You're like, actually, B means you're getting the grade you deserve, and A is like they're throwing a dart at the dartboard and adding it to the grade you deserve. And like maybe you're getting a 40 or maybe you're getting 100. And some people just like live on the edge like that. But what if we had to put in words, what's the difference between A and B? It's not expectation. In expectation, they're exactly the same. Now, I don't want that in word. I want another term for it.
Spread.
Spread. Spread is a nice natural term. There's a lot of spread here, and there's a little spread here. And it'd be nice if we could come up with a quantification of spread. I'm going to give you a slightly simpler example where we can go into exact numbers. Here are 3 distributions with the same exact expectation. They all have expectation of 3. But the difference between these 3 distributions is how much spread that they have. You know, this has a ton of spread, and this has very little spread. I want you guys to invent what would be a good definition for spread. So, how can we define spread? And I'm going to give you guys a second to think about it. Talk about it with the person next to you. I'm going to give you 3 whole minutes to think about how would you quantify spread. And to make it easy, you could think about this as being like 10,000 unique numbers. And this is just the histogram of those 10,000 unique numbers. That might make it easier to think about quantifying spread. OK, let's get ideas. Let's throw them on the board. How could we do it? And I don't know if it's helpful, but I imagine we have a whole distribution, and I want us to think about 2 pieces of this distribution. Here's a chunk of the probability that's a certain distance from below the expectation, and here's a chunk of probability that's a certain distance above the expectation. How can we quantify this spread? Looking for maybe somebody who hasn't said something today. Yes?
Well, you can start by taking the distance from each data point to the expectation.
OK. let's talk about the distance to the expectation. I like that because, you know, when there's high spread, you have these things that are really far away from the expectation. When there's low spread, you have things that are really close. So distance seems like a very good idea. There's lots of ways you can measure distance. Let me give you a bad one. You could take the value and you could just subtract off the expectation. And we can say we just want the average of all those. You know, give me the average of the value itself minus the expectation. So like over here, this would be like a +5 and this would be a -5. Why is that a bad way to measure distance? Yeah, it's like these positive ones will lead to a large value and these negative ones will lead to a negative value, but if you take the average of these positive and negatives, they'll cancel out. So what's a better way of calculating distance than just taking the value and subtracting off the expectation?
Taking the absolute value.
Oh, okay, I've heard two good ideas. You could take the absolute value. So you take the distance, you subtract off, see how far it is away from the expectation, and if it's negative, you make it positive. And then if you take the average of that over all of your distribution, that would work. And somebody else said, don't do that. I want to do the average of the squared distance. So take the difference between x and its expectation, square it, and I kind of want to average that over my whole distribution. And expectation is my function for averaging over the whole distribution. Which one is right? They're both right. They're both right. If we had gone back in time and we were inventing variance, we could have made either of these the definition of variance, and they both would have been reasonable. People happen to have chosen this one, though I think this one would have made absolutely good sense. To get the pun? It's absolute. Okay, question.
Different fields that use different definitions of like just kind of stuff. Like sometimes things prefer absolute values, sometimes they prefer squaring.
There's times when you're thinking about distances in lots of fields, like when you get into machine learning, there's lots of times people think about distances. And people call this the L1 norm, people call this the L2 norm, and there's times when you might care about these different distances. There's even other ones beyond these two. And people have argued about them in lots of different fields. And in probability, they just happen to have chosen this one. And I think every time people talk about variance, I've seen them talk about it in terms of this distance measure. Yes?
We like squared more because it punishes stuff that's further away, which seems worse.
Yeah, you're right. It does punish things. So like if you get really, really big differences between the expectation and your value, when you square it, it's going to look really, really bad. Whereas if you get small numbers and you square it, it's not so bad. So it does have that property, whereas the absolute value one doesn't punish being too far away as harshly. So they do have this qualitative difference. And that's a really nice, maybe that's a good reason for choosing the L2 norm. Anyways, long story short, people define this measure of spread that people call variance, and they define it to be over your whole distribution, on average, what is the distance of values to the expectation? And I'm going to use this shorthand form for the expectation of x mu, because otherwise you have too many expectations of x's there. And just to give you an idea of what's going on here, if you had a data set and you had to calculate this, let's say x here is 25, x minus the expectation, so 25 minus 60 will be a negative number. When you square it, it will be a large positive number. And you could keep doing this for every single data point in your data set. If either you loop over your whole data set or you take every data point and weight it by its probability, you would get the average of the distances of every point in this distribution to its mean. And you could calculate it for this, and you could say it's 52 points squared. That's the units. What's a point squared? I don't know. That's just what the units are. Well, it turns out a lot of times people are like, I don't like these points squared. So there's this other definition of spread, standard deviation, which is just the square root of the expectation. It's just taking this number, square rooting it. That's the standard deviation. So variance, it's defined to be the expectation of the distance from points in your distribution with its mean of the distribution. And distance is measured by taking the difference squared. It's a formal definition of spread. It has other names. Somebody asked earlier in class, what if you had other moments? Well, it turns out variance is the second moment. Expectation is the first central moment. Variance is the second central moment. You can imagine that there's moments beyond this. We're going to stop at variance in CS109. Okay, this is an idea. Normalized histograms are approximations of probability mass function. We'll talk about that more another day. I did want to talk about how you compute this in the real world. That is the definition we really cared about. We really cared about having the average of the distance from the mean. Now, earlier in class, I told you there's this law of unconscious statistician. And the law of unconscious statistician says, if you apply any function to an expectation, like if you want to know the expectation of any function of your random variable, that this is equal to the sum of all the values, just apply the function to each of those values and then multiply it by its probability. That was the law of unconscious statistician, and this is the very first time we're going to use it. I want to come up with an easier way to calculate variance. Our function here is take x, subtract off its mean, and square it. That's a function. And so we can use the law of unconscious statistician, and it's going to enroll expectation like this. It's just going to apply that exact same function to every single value. So every single value, you're going to subtract off the mean and square it. And you're going to do that before you multiply that probability that x equals x. If you applied this law of unconscious statistician, you can take this expression and just do a little bit of algebra, which I'll leave for you guys to do at home if you're curious. But you can just expand this term, kind of regroup it into different parts, take those groupings and simplify them again. And you end up with, well, at this point, you enter this expectation of x squared, which we'll talk about in a second. Leave that in there. And if you just simplify this, like this is the mean times expectation. Well, expectation is what we defined the mean to be. And this thing just simplifies till eventually you get that if you want to calculate variance, you could calculate this equation. That's semantically what we care about. But we can derive that there's this equivalent way of calculating variance. And this is the one that's so much easier to do. And this calculation looks crazy. It looks like you have the same thing multiplied or subtracted from itself. You have expectation of x squared, and you're subtracting that from expectation, wait for it, x squared. And that's the equivalent of that. And that feels like it should be 0, but it's not 0. This is the expectation of x, and this is the expectation of applying the squared function to x. If we use the law of unconscious statistician, we can know what the expectation of x squared is. The expectation of x squared is going to be equal to, using the law of unconscious statistician, expectation of x squared is going to be the sum over all the values that x can take on, square that value before you multiply by the probability that x equals x. That's what the expectation of x squared is. It's different from taking expectation of x and then squaring it.
That's the same thing as squaring expectation. So before, in the last slide, you had, you had it outside. So I guess you're squaring the expectation and the x in this case.
Yeah, here you're taking each of the values and squaring it when you're weighting it into the sum. And in the other term, you're calculating the normal expectation and then squaring it afterwards. And it turns out it really does matter whether or not you square each value versus whether if you take the expectation and square it. And this thing is called the second moment. It's just a funny name for something that we use in our calculation of variance. And it really comes down to this. If somebody asks you to calculate variance, you're going to use that equation. Okay, we are at the end of today's day, and the big takeaway is we've defined variance. We now define it to be this thing, and you can now standard deviations define it to be the square root of variance. We'll pick up this conversation on Wednesday. Thank you guys so much for such a fun class. Come back on Wednesday. We'll continue this conversation of random variables. You'll learn about the Poisson, one of my second favorite random variables of all time. Have a great day. Come back on Wednesday. See you later. CS109.